All right, well, welcome everybody and hello to our webinar. Today we're going to be talking about comparing and contrasting artificial intelligence and auto scoring in sleep medicine. And this webinar is presented by EnsoData and Cadwell together. All right, so my name is Jason Tucker. And I want to thank you all, and at last count there are about 300 people registered for this webinar. I want to thank you all for taking time out of your busy schedules to spend some time with us today. But before we get started, we've got a few important housekeeping items to address. As I mentioned, we've got hundreds of people signed up for today's webinar, so we're going to keep all lines muted to minimize background noise. However, we will have some time at the end of the presentation to answer questions, so please feel free to type in your questions during the webinar, and we'll get to those at the end of the presentation. Okay, so quick introduction for our presenters today. So we've got Sam Rusk. Sam is co-founder, president, and the head of AI at EnsoData. He's responsible for deploying AI in the clinical setting, as well as leading EnsoData's research initiatives. Sam co-founded EnsoData after receiving a Bachelor of Science in Electrical Engineering from the University of Wisconsin in Madison, where he developed a passion for signal processing and machine learning. Sam is currently a consultant to the AASM AI Committee, where he helps bridge the gap in the world of AI and medicine. Sam envisions a future where AI enables accurate and affordable healthcare for all. Mary Blevins is a registered polysomnographic technologist, or RPSGT, and holds a certificate in clinical sleep health. So Mary has worked in sleep medicine for over 15 years as a sleep technologist, sleep educator, and manager. Mary has worked in private, hospital, and university sleep centers, including University of Wisconsin and OHSU in Portland. Mary has conducted both clinical and research sleep studies on patient populations ranging from infant to geriatric. Mary now brings her passion for helping sleep disorder patients to her work at Cadwell, providing application support assistance to sleep physicians and technologists, and providing input to Cadwell's ongoing product development programs. And then Cindy Braden is EnsoData's Senior Vice President of Sales. Cindy has over 20 years experience in healthcare, from surgical sales to leading growth teams of a cloud-based electronic health record software company, to her current role at EnsoData. Cindy's vast experience in healthcare uniquely equips her to effectively collaborate with multiple members at various levels within organizations to understand what makes them distinct and discover solutions that help them achieve organizational goals and to support their teams. Okay, so one more piece of housekeeping. We do have some conflicts of interest to declare. Sam is obviously, as president and co-founder of EnsoData, he does work for a sleep medicine company. Likewise, Mary, as an employee of Cadwell, also works for a sleep medicine company. Cindy Braden of EnsoData also works for a sleep medicine company. And last but not least, I work for Cadwell. I'm the global marketing manager at Cadwell, so I also need to disclose that fact. Okay, so what are our learning objectives for today? Well, we hope to give you some understanding of artificial intelligence, machine learning, and deep learning, so providing some definition around those three, because there's often some confusion as to what those three are. The differences between those three types of AI applications, some examples of each, and definitions of auto scoring and AI-assisted sleep scoring, and differences between those two types of methods. So in terms of the format, I will ask some questions of Sam, of Cindy, and of Mary. They're going to provide their response to those questions, and then if needs be, I'll go back and ask some clarifying questions as and when appropriate. So that's the format. Okay, we thought it might be interesting to give ourselves a timeline of sort of the process or progress within sleep scoring. So way back in '68, R&K published the first manual for the sort of standardization of scoring of sleep stages. The next milestone was when sort of computers got involved to analyze PSG studies. That sort of started around 1995. And then in 2007, the AASM manual for the scoring of sleep and associated events was released. And then more recently, in 2017, the FDA clears sort of the first artificial intelligence assisted sleep scoring software technology. And then more recently still, in 2021, the FDA clears AI-assisted scoring for a sort of broader group of patients, pediatric patients, ages 13 and up. So sleep scoring has been around a long time, and it's been developing throughout that sort of life. Okay, so having given you some idea of the sort of progress, Mary, perhaps you could take us back and tell us, how it all started. What is manual scoring?
Well, so if we go back far enough, we used to actually score PSGs very literally by hand. We would mark the stage of sleep on each page of paper, and then we'd go back and mark the respiratory events. Then doing a hand tally of those events and calculations to be able to get the report. Digital polysomnography significantly reduced the tech time doing these processes and allowed us to enter in and edit this information on the computer and let it tabulate for us. When we would then score a record, we would review the record and manually mark all sleep stages, arousals, respiratory events, limb movement, and cardiac events. And that means a lot of number pad and click and dragging, highlighting to mark all of those events. Yep, there we go. Sorry about that. So frequently we'd find that most of our users use a multi-pass system where we start at the beginning of the record and mark each stage of sleep and any visible arousal within a 30-second page view. Then we would change our paper speed, montage, maybe even the layout of the windows, and again, start from the beginning of the record and run through to the end, marking respiratory and/or limb movements. They typically do this at a higher paper speed, like a 120 or 300 seconds per page, so that they have a better view of these events that occur over longer periods of time. Some users may even do limb movements in a separate pass and or even do another pass with a detailed view of EKG. So the manual scoring process has been around for over 50 years, and it's been difficult to replicate with an automated process because of its strengths. While it does require a lot of technologist time, technologists get a feel for each patient and record, and they can then adapt to what they see occurring on each patient, and they can also make sure that their scoring matches the preferences of the providers they work with. Now, some of the drawbacks to that are that the process is so labor and time intensive. So that time could be spent assisting directly with patient care, which is usually what draws techs to the field. Also, while techs develop a feel for what their providers like to see, that can make it really difficult for even an experienced tech to move to a new facility where provider preferences can be different. And so it doesn't help with the industry's overall goal of standardizing how we score records.
Okay, so just help me understand that. So sleep techs go through literally hundreds or even thousands of pages of data, once or more than once for every patient.
Yep.
Okay, so what sort of tools are used to make things more efficient or things easier?
Well, a lot of labs are using some level of a software-assisted auto scoring. Software-assisted auto scoring uses a conditional logic, like an if X then Y type of scenario, which is more traditional method of programming. So we use machines to analyze things typically evaluated by people using those rules, but instead using the machines to get some automation out of the process.
Okay. All right. So, Cindy, could you give us some perhaps some real world examples of software assisted automation?
Yeah, of course. So unlike Mary with her technical background and Sam with his electrical engineering background, my major in college was Spanish and communications. So I tend to think in analogies, and I'm here to try to relate that a little bit, although I will say I didn't understand any of this until Sam initially broke it down for me, so he does a great job explaining things, but I'm here to kind of break it down with some examples. So if then, I think this is software that we probably see all over our world. Once you start thinking about it, you're going to see it all of the time. You're going to start analyzing, which at least if you're like me. So stoplights are a good example. There's different forms of if then software assisted automation for stoplights. If you live in a rural environment like I do, they have those sensors in the road. So you can be sitting at a stoplight and feel like it's going to take forever for the light to change. But if no cars are coming from the other way, the software recognizes that there's somebody waiting at the one spot and then changes the light. In areas near hospitals or where you have a lot of ambulance and emergency vehicles, you guys will see the lights that will pick up on the sirens. There's a signal that is in the emergency vehicle, so it's the same thing. If the signal is picked up by the software, it adjusts all of the lights at the intersection to provide safe passage for the emergency vehicles. Something that I did not know, because my son is 16 and they did not have really cool baby monitors with assisted automation back when I had him, but the baby monitors these days have software in them where they're monitoring for different things to happen. So one of them that I saw has the ability to monitor if the baby is moving down to even taking breath. Then if I think there's like a time frame, if it's like 16 seconds where there's no movement at all, no breath, an alarm alerts so that you know you can go check on your baby to help cut down on SIDS and stuff. So the technology and the automation is really amazing and really useful in so many situations. I think close to what we see with software assisted automation for sleep scoring, a good example is the Scantron test. So if you ever took your ACT or SAT or even some of the tests at school, you know, the teachers are very, very strict on filling in that circle, filling it completely. Don't get into another circle, because the software is able to say, you know, here's the right answer. If it's filled out, it's correct. If a different circle is filled out, it's incorrect. So if you think about all of those tests that are done, and if somebody had to manually score those, how helpful the software assisted automation can be.
Cool, good. Okay, so sounds like it's all around us, but Mary, you know, how would you use this, or how is this used in sleep medicine?
Well, typically with the if-then rules, they're pre-configured within the diagnostic software, but users may still be able to edit them. Rules might be things like if the SpO2 decreases by X%, then mark an oxygen desat. If the leg channel has an increase of 8 microvolts or more for at least half a second to 10 seconds in duration, then mark a limb movement. If there are foreign limb movements separated by anywhere between 5 to 90 seconds, then mark as periodic limb movements. Or even if the heart rate was above 90 or below 60 for some amount of time, then mark as bradycardia or tachycardia. So many facilities today will then utilize a hybrid approach to scoring, where they auto detect some events, but then manually score others. Software-assisted auto scoring may improve tech efficiency and let techs focus on scoring more complex events. Those events are some of what make software-assisted auto scoring less effective overall. They can be things like respiratory events, sleep staging, arousals, even cardiac arrhythmias like atrial fibrillation. They may not have the same accuracy when detected by the if this then that logic. So some patients may have more complex rhythms and not work well with software-assisted scoring as well, like a non-alpha generator or alpha-intruded patients. Additionally, artifact, faulty leads, bad placement, or high impedance signals can also complicate the effectiveness of that software-assisted auto scoring.
Okay, so just to make sure I've understood that, so it sounds like there's some areas, or quite a few areas, that traditional software-assisted auto scoring is less effective than manual scoring. So how does that? Okay, I guess that takes us to artificial intelligence and some of the differences that we might get from sort of new technology, new methodology. So, okay, got it. Cindy.
Perfect. Yes, I'm going to jump in here. So this is the audience participation part of our presentation. You have to look at these 4 faces to get a sense of, let's see how good our human eyes are compared to artificial intelligence. And look at these 4 faces. I'm gonna launch a poll here where you can pick which of these faces is not actually a real person and was generated using artificial intelligence. So everybody got when I launch the poll, you don't get to see the faces anymore. So pick your person. Ready? Okay, here you go. Okay, so give your votes. Is it face 1, 2, 3, or 4? Which one? Oh, you guys are voting fast. Good thing we gave you a heads up that it was coming. All right, 60% voted. Go quick, quick, quick. I'm always so curious to see. All right, we'll give it 3 more seconds. 1, 2, 3, or 4. All right, I'm gonna close it. Everybody thinks number 2. All right, 2 with a close number 3. All right, I cheated. So all of these were created by artificial intelligence, which really just blows my mind. There's actually a website if you want to go play around with it. I did this with my son when we were driving the other day, and I was trying to keep him from staring at his phone and engaging with me. He pulled up, this person does not exist. And if you keep refreshing it, it keeps generating a new face. And he was like, I swear I know some of these people. But it gives you an idea of how good artificial intelligence can be based on the information that's plugged in, and then run through the algorithm and gives you these great outputs that obviously these all look very much like a real person, but I promise you they are not.
Sneaky trick question.
I know.
That's not. Okay, so before we dive into AI or AI-assisted scoring, we need to understand, I think, what AI is. So let's turn it over to Sam, head of AI at EnsoData, hear what he has to say about artificial intelligence, and give us a little bit of a dive into machine learning and even deep learning. Okay, over to you, Sam.
Awesome. Thanks, Jason. Thanks for joining today, everyone. So yeah, what is artificial intelligence? What is machine learning? And what is deep learning? So AI is a broad category that represents many types of algorithms. And so machine learning is a subset of those AI where you actually use statistical-based approaches. And then within that, you have deep learning that leverage the neural net architectures. So this is, I think, moving on to the next slide, Jason. This can be an important hierarchical relationship to understand as you hear and learn more about research and tools with this terminology. So starting at the top, what is artificial intelligence? it's any technique that enables computers to mimic human intelligence using basic logic if-then rules with varying degrees of complexity. So examples that you might see of this are rule-based systems or closed-loop systems, and you might see these in simple computer programs or other kinds of electronics. Within that, you have machine learning, and so this is a subset of AI that includes statistical techniques that enables machines to improve with experience. And so what that means is that they can really learn from historical data. Examples of these kinds of models are decision trees, if you've heard of those, clustering algorithms, and basic logistic regression, which is used often in the medical literature. And then lastly, what is deep learning? It's a subset of ML that utilizes the artificial neural networks to iteratively learn complex representations that connect an input data to an output data. So where these deep learning models allow us, what they really allow us to do is represent high resolution features from the data. And so in images, these models are used to interpret the pixel level information like texture or color. But in the time dimension and in sleep, they're used to interpret waveforms, shapes, and different frequencies that you see in EEG or even respiratory signals. So the same way that we can learn to classify an image, we can learn to classify a sleep waveform as well. Awesome. So when building solutions for healthcare, we often leverage the machine learning and the deep learning methodology. So what is machine learning and how does it work? Machine learning models learn through an iterative process where you have a model with parameters and an optimizer that iteratively trains the parameters to minimize the loss or the difference between the true labels and the predicted labels. And so as you train the model with multiple passes over the data set, the model accuracy improves with each iteration. Similar to how we learn as humans from experience, the model learns the more data it sees. And so this is a graphical representation of how you have a model and you are cyclically optimizing the parameters with the ground truth information. And so the most common form of data in healthcare that we use for machine learning is historical data. And this allows us in the algorithms to learn from data that has potentially been accumulated from hundreds of different hospitals, different physicians, devices, and other contextual information.
Cool. Okay, Cindy, can you give us that back again in a language, in sort of different language that maybe a more layperson's language?
Yeah, and Sam will have to correct me if I'm not explaining it well, but this is the diagram that I had actually made as I was working with some groups that we were working with that had specific questions about machine learning, and I wasn't entirely sure how to answer that. So Sam was able to educate me. We had a couple of the other AI engineers write out a paragraph, and then I put this together with some other stuff I found online. So this example in perspective with what we do in sleep medicine, you'll see that there's studies up there in the corner. We have the ability to look at studies that have the data there and that have been scored by an RPSGT and reviewed by a provider, right? So we kind of have truth. If you see the dotted line, we're able, as Sam mentioned, to build and test and iterate on the algorithm, the model, based off of knowing what the truth is. So we can plug, after we put the algorithm through the existing truth or the studies that have been scored and help build the model, we can then take an unscored study, plug it in the model. The algorithm can take a look at that information and make its prediction. And then it has the ability to compare it to truth, right? I know that having an RPSGT review it, adjust it, we have the ability to know how good the prediction was compared to how a human would score it, and mimic what did you say, Sam? The neural network, right?
Yes.
That's how humans learn, right? So then we can learn, the parameters can be adjusted, the model can change, and it goes through. So if you think about this, as Sam mentioned with the neural network and how humans behave, there's all sorts of information that comes our way that could shape how we learn things, which is very similar. There's almost a direct analogy. If you think about it, it's probably way simplified, but people can tell you information, right? Like sometimes we listen, sometimes we don't. You can watch how other people do things and the result that happens. And then you also have the ability to do things yourself. You can touch a hot stove and then you know the pain, you know what it looks like, you know the pain that you feel, and all that goes through your neural network in your brain, and then you're going to adjust your outcome based on it. So you've got all of these different datas and parameters that are set out there. You're going to process them, and then hopefully you're going to adjust your behavior moving forward. So that's how the human neural network works. So as Sam gave the great example, especially in healthcare, we have all of this previous information that we're able to learn off of and help build predictions off of, mostly which was the previous information is based off of human information and intelligence, right? So that allows the machine learning to try to mimic human intelligence and then hopefully continue to get better over time. So Sam, did I explain that accurately? Because you should say yes before everybody puts that into their neural network and takes it as truth.
Just check that.
No, absolutely. Yeah, neural networks were inspired by the biological neural networks of animal brains, and so that it's, you know, having multiple layers of neurons that have connections, definitely inspired by the same way that humans have evolved.
Okay, good. Thanks, Cindy.
Awesome. So moving on, going a little bit deeper on machine learning, we have three major families of learning paradigms in the machine learning world: supervised learning, unsupervised learning, and semi-supervised learning. Supervised learning is your more classical form of machine learning, where you have an input data and an output data, and the models learn to minimize the loss function or the difference between the predicted label and the true label. So this is generally the domain where a lot of healthcare applications fall, given its discrete predictable output, where you can measure accuracy or sensitivity and specificity based on what kind of endpoints you have. Unsupervised learning is the collection of algorithms where pre-assigned labels are not provided for the training data. So as a result, these algorithms self-discover naturally occurring patterns in the training data that can be useful for exploring large or unstructured data sets. These tools are how we find relationships within the data that help us to investigate further when you're first starting a problem. And then finally, semi-supervised learning combines both of these approaches, and you take a small amount of labeled data with a large amount of unlabeled data. And when used in conjunction, a small amount of labeled data can produce considerable improvements in the learning accuracy. And so this can be especially useful in the healthcare setting, where collecting data can be expensive or difficult, or sometimes even exploratory in nature. So being able to leverage data that's unlabeled can be very useful.
Okay.
Awesome. So looking just three quick examples of these, as you might be able to comprehend them a bit easier. The first one is an example of supervised learning is in classical image classification, where you have an image of an apple, and then you have a basic neural network, and the model aims to predict which class of fruit the image should be. And that is classic supervised learning. In unsupervised learning, a popular example are autoencoders, where autoencoders take an input image, compress the representation in the model, and then relearn the same image out. And so this forces the information from the image to be represented in a compressed format, and then can be used for features and other tasks, or even clustering. And so that can help you really explore data using an unsupervised approach. And then lastly, in semi-supervised learning, a popular example are GANs, or generative adversarial networks. These model types are what are used to generate the very realistic looking images that you saw earlier. And they leverage both labeled data and unlabeled data to create these synthetic images that are now amazingly foolproof. So pretty cool to see how those have developed.
Sam, can I ask a question? I think supervised is the easiest one for me to understand. So those labels for like identifying a fruit, the labels would be like apples are round, apples are red, apples react this way to the light. Like, I know that's like super simplified in this example, so that when they look at a banana, it's like it's not round and it's yellow type of a thing. Is that what you mean by labeling the labels?
Yep, exactly.
Okay, I think I got it. But Sam, can you walk us through some examples? Yeah, let's take a look at a few, and then perhaps you could walk us through.
Yeah, absolutely. So I will go through a few examples here, both as we see examples in the real world, but then also examples as we see in healthcare and in research. So AI has the ability to mimic human decision-making, as we spoke about. And now with increasing levels of complexity in the world, technology solutions that we interact with every day are necessitating it. So we see companies like Netflix, Grubhub, and Amazon all leveraging machine learning tools at scale today. So running through these examples, Netflix can learn from its entire user base of people's movie preferences, similar archetypes of movie watchers, and they can recommend new categories of movies to watch and different things that you might like. This kind of learning is possible just due to the millions of movies that users have watched in the past, and so that's how they're able to continuously improve the experience. Grubhub uses a very similar methodology to recommend new restaurants or other items that others have liked. They're able to improve the user experience that way, very similar to how Netflix might. And then lastly, Amazon Alexa is growing in its complexity and how it's using machine learning, using more deep learning solutions now, but with its really improved voice recognition and being able to recommend new songs or automatic reminders, how Amazon Alexa is integrating in with everyday life is fundamentally based on machine learning. And so while there are many ways that we can put AI to work by finding your next song or your favorite movie, there are even more impressive ways that we've been seeing it applied, especially when you start leveraging the deep learning tool sets.
Cindy, do you think that's, do we think we've hit the nail there, or do you want?
Yeah, I think these are hopefully examples that we've done a great enough job that everybody's like, oh yeah, I get it. I did have to say I was watching a TV show that I did not like the other day on Netflix, and I fell asleep, and it ran through a bunch of episodes, and I was like, oh no, Netflix is gonna think this is my type of program because I fell asleep. I should have turned it off before I fell asleep, because now it's up in my algorithm. It thinks I like that show that I did not like. So keep that in mind if you're looking for help from your AI.
Well, maybe you need to connect your TV up to your baby monitor.
I gotta give yeah, exactly. Then it could just turn off, or I give it a thumbs down.
There we go. Okay, so a couple more examples, Sam, in terms of deep learning.
Absolutely, yeah. A couple of deep learning examples that we have. The first example is deep learning-based lane detection. And so lane detection is an integral part in building autonomous vehicles and assisted driving. And so you can see in the image that the algorithm was able to correctly identify the driving lane highlighted by green. This allows the system to alert the driver of an upcoming turn or if they might be drifting to one side of the road, and results in maintaining safer roads and transport for everyone. And so the deep learning model architectures allow us to learn this pixel by pixel mapping of the road, where tasks like this would have been very difficult even 20 years ago. Another clever use of deep learning is in detecting high fire risk geographies by leveraging satellite imagery. There are tens of thousands of satellites continuously orbiting the Earth, and AI has been able to pair historical satellite imaging with areas where forest fires have occurred. And so the systems are able to learn and detect patterns that lead to the higher likelihood for forest fires. This obviously allows the authorities and fire departments to appropriately allocate resources to mitigate those. And so similarly here, the deep learning model architectures allow us to learn a high resolution map of fire risk in a way that would be very difficult in the past. And so these are just a couple of ways where we see deep learning being used in the real world today.
Cool, Cindy. Anything to add to that there?
Yeah, the only thing I'll add here, I love this second example, and again, the way I think of as analogies and how it pertains to information in healthcare, right? So we've got satellites just watching the world when there are no fires, but they're collecting that data, and then when a fire happens, they have the ability to go back a little bit and say, what were the conditions, or what is the data that we had prior to the fire happening, and then being able to learn so that we can predict when those conditions happen again, that a fire is likely to happen, and hopefully eliminating it or getting ahead of it. This is the kind of thing that just gets me really, really excited about what the software is going to be able to do for the world. And then in healthcare, where we've got all of this data and all of this health information, and then things happen, being able to take that information and going back and looking at it and plugging it into the AI so that we can get really good at predicting things before they happen to people. So I just think that's a really great example that runs a bit parallel to how the previous data is used monitoring the earth as well as in patient healthcare.
Okay, Good, super. So Sam, now let's bring it home. I mean, can you give us some examples of how machine and deep learning are sort of bringing improvements to healthcare sort of now, today?
We certainly can, and I'll bet everyone's mind is already racing for how we can use this to improve healthcare. So covering a couple of studies here that leverage machine learning. A study from 2017 aimed to predict 30-day all-cause readmission for heart failure patients. The input data was composed of various different sources from the electronic medical record. So they had demographics, age, sex, and ethnicity, socioeconomic status, medical history, characterization of heart failure, readmission and discharge medications, vital signs, and laboratory treatment data. And they used all these parameters to build multiple statistical and machine learning models. And comparing to the baseline metric or the baseline EHR derived predictors, they weren't able to show an improvement, but basically showed the same approaches. And really, we're just kind of suggesting how you can study these kinds of outputs in these different readmission metrics using EHR data. Moving to the second one, a study from 2020 where different machine learning models were leveraged to predict post-operative emergency department readmissions. So similar to the previous use case where they're taking variables and metadata from the EMR to predict readmissions, except in this case, they're looking specifically at post-operative patients where the complications that might cause the readmissions could be different. And they showed that lab features had the highest discrimination, whereas surgical and demographic features had only moderate discrimination. And so stepping back and looking at these two examples together, they're very similar but rely on different data for different tasks. And so each of these applications of machine learning requires investigation and engineering to appropriately evaluate and validate these clinical endpoints. So these are a couple examples that we see machine learning being applied in healthcare.
Cindy, do you want to add anything or give us a couple of other examples, or do you think we're good?
I don't, but I know as we go through these, this is just a great example of comparing it to the fires, right? We have this information, and if we can get ahead of readmissions or incidents with patients, hopefully everybody on the call, this is the kind of thing that you're here to learn more about.
Cool. So we touched on machine learning. Let's switch into deep learning now, Sam. So help us grasp a little bit more about deep learning.
Yeah, so a few awesome examples using the deep learning model architectures in healthcare. One that you may have seen in the headlines a few times is AI-based sepsis prediction. So sepsis is a major health crisis and was one of the top 10 leading causes of death in the US in 2010. And so sepsis is defined as a dysregulated host response to infection in the body, often in hospitalized patients. So basically an infection that takes over the body. It can go easily undetected due to how similar the symptoms are to many other diseases. And so detecting sepsis early is extremely valuable and can directly save lives. And so in this study, researchers at UCSF have been working on this, building AI models to predict sepsis by reading in the standardly collected vital signs at the ICU bed. And remarkably, they've shown that AI can predict sepsis shock onset 4 hours before it happens with an area under the curve of 96. This allows clinicians enough of a warning time to treat the patient accordingly and hopefully eliminate sepsis altogether. Moving on to the second example, another application increasing in its clinical adoption is in skin cancer detection. And so initially developed at Stanford and published in Nature in 2017, researchers showed that AI models trained on 129,000 clinical skin images and tested against 21 board certified dermatologists had the same performance as the average dermatologist. And so while AI can't make you go see your doctor, tools like this can automate and democratize skin cancer screening to anyone who has a smartphone. And as we think about addressing healthcare disparities in rural settings or around the globe, effective screening and diagnostic tools like this will have a massive impact on how healthcare can be delivered effectively and at scale. And then an example, a more recent example that may be affecting you today is with regards to the COVID-19 pandemic. Researchers from MIT were able to take audio recordings of coughs and accurately detect coronavirus with close to 95% accuracy. They've built a tool where anyone can log into, record a cough, and mark whether they tested positive for coronavirus. And the AI was able to parse out subtle shifts in cough and frequencies otherwise indistinguishable from the human here, which is quite remarkable. Even the best doctors in the world can't diagnose COVID with just their ears, and so these technologies are proving to open doors that were previously thought impossible. And so this application brings up two main points. One, capabilities like this are can be used for far continuous and widespread screening for diseases like coronavirus. And then secondly, this highlights the ability of AI to go beyond human perception. These models can detect patterns that we can't sense with our 5 senses, and so it creates a lot more information from the data that we already have. And so this is just a few ways that we're seeing deep learning being investigated in the medical community.
I'm going to jump in quick here too on the second example, Sam, because you bring up a good point, right? Like the patient needs to go see the doctor to be treated, but we can't make patients go see the doctor. So having some sort of screening tool that can help alert patients so that then they go and get treated. And then, as you mentioned, getting access, more equality with access. It's the sort of thing that AI can do. And then along that, if you have data on your patients, right, we could probably also use AI to flag which patients are less likely to go see a doctor that might be of higher risk, and maybe even use the results from that for doctors to proactively reach out to the patients and flag them and bring them in as well. So just everybody can tell I geek out on this stuff, but there's just so many cool things that AI can do to help, not only with the screening, but flagging the patients and getting them into the doctors.
Okay, cool. So let's bring it even closer to home now. So Sam, could you help us understand or talk a little bit more about how AI is being used specifically in sleep medicine?
Yeah, absolutely. We won't go into the AI's application in sleep too closely, but just covering the 3 basic ways that you can use AI to investigate sleep, sleep medicine, and sleep physiology. And so the first is in studying what and the why of sleep, trying to understand what the patterns we see, like K complexes or spindles, and how those actually represent the neurological physiology, and how we can really understand those kinds of waveforms better. The second is in investigating the role in sleep in disease and consciousness and other physiological processes. How do all these different parts of the human body that we can observe work together? And we can use these kinds of machine learning and AI-based tools to investigate those. And then third is to investigate the different sleep disorder endotypes. And so understanding the disease pathways and the different representations that can fall in different populations. And so trying to understand how these diseases actually characterize at a population level. And so those are a few of the ways that we can think about using AI in sleep medicine.
Okay, cool. So now we know what auto scoring is, what AI is, what machine learning is, and we know a little bit about deep learning. Can we better understand the differences between software-assisted auto scoring and AI-assisted auto scoring of sleep studies? So, Mary, could you remind us how software-assisted auto scoring of sleep studies sort of actually works?
Absolutely. So software-assisted auto scoring brought users the ability to establish rules that they can configure, and if this, then that criteria. The introduction of this functionality really improved scoring times for labs and allowed techs to have save time kind of repeatedly scoring those oxygen desaturations and heart rate changes so that they could focus on those more complex events that needed the tech's specific knowledge. But it may not work as well on certain patient populations or certain event types that may require a more powerful analysis. Okay. And so that now brings us to that contrast between the software-assisted scoring and the artificial intelligence-assisted scoring, where it doesn't follow one set of rules. Instead, it uses machine learning. The algorithm is able to identify the patterns in the waveforms, and as a result, score the studies. And since the algorithm for AI-assisted scoring is complex, individual settings and mapping changes can drastically improve the performance of the AI.
Okay, Cindy, anything you want to bring in here?
I think they did a great job explaining it. Mary always explains things well, but if you flip to the next slide, since we showed manual scoring and examples of automation in scoring, ta-da! When AI scores the studies, it looks the same. It's just done. So the artificial intelligence goes through, scores a study, flags everything through the algorithm based on the machine learning from the previously scored studies and the algorithm and how it was built. And then a technician just comes in and takes a look at it. And as Mary mentioned earlier, really flags those things where they can lean into their area of expertise. I was peeking at the question somebody asked about pediatrics. That is a great example where things can be more complex, right? So if you can get some sort of automation or AI to go through and flag other things, it really allows you to pay attention to those tricky things for pediatrics. And the answer to your question is yes, it is used in pediatrics as well. So
thank you. Back to Mary.
Yeah, so when we're looking at the strengths and weaknesses, with AI-assisted auto scoring, we gain the ability to get close to scoring studies like a technologist might and can easily scale. But in order to get to that level, the algorithm requires a lot of data and a lot of programming to obtain accurate results, and then continues to grow and learn from regular technologist feedback.
Super. Okay, so we got, wow, we're pretty much on schedule. So, okay, let's see what questions we have. And let's ask the panel some of those questions. Cindy, are you able to see the questions?
I am. Do you want me to fire them off, Jason?
Yeah, go ahead and let's, well, some of them may be for you, but go ahead.
Probably not any for me. The first question, Mary, I think this one's for you. What if limb movement and periodic limb movements are absent? Then is the scoring still possible?
Are we talking more like a manual scoring software system?
I think it was typed in yes with the manual scoring.
Yeah, so the advantage with the manual scoring is that techs are always able to go in and kind of make that determination themselves. So where we were discussing previously where, with even software assisted scoring, it's always critical to have kind of ideal lead placement and making sure that those sensors are properly placed or in great condition. And so with manual scoring, you have the ability to just go over everything yourself and make that determination. So in some instances, they might have noticed a lead fell off, but they can see on the video that a patient is kicking and can see maybe a shift in the EEG as well. And so they can start to make some of those correlations themselves manually, even outside of any of the AI assisted scoring or software assisted scoring.
Perfect. All right, Sam, I think this next one is for you, specific to AI. Can we use AI with CPAP compliance? Oh, I love this question. You're thinking like we're all thinking. Maybe even in the prediction of CPAP titration success, if it can tell by a cough if somebody has COVID, seems like it could likely predict breathing patterns, depth, etc.
Yeah, absolutely. There's a couple of different ways that you can use AI with data like CPAP. I think for one, you can certainly think about using, CPAP usage data to predict when people are, weaning off of the treatment or if they're starting to use it less, and that can be helpful for managing treatment on an ongoing basis. But yeah, I think the more exciting way is to think about how we can characterize responsiveness with those or with CPAP from the either the in-lab or the HST studies, using the diagnostic waveforms and trying to understand how, if you can predict whether someone will be successful or not using CPAP as a treatment. And I know that there's some pretty recent publications that have been investigating that, looking for those different markers. So yeah, certainly more ways to use and predict CPAP from the studies.
Perfect. Next question. Oh, Mary, maybe? No, let me read it, and then you guys can tell me. This is how people can tell I'm not an RPSGT. While using assisted scoring, which parameters should the technician pay more attention to? And so maybe Mary, and then Sam, maybe you for the second part. What event is the algorithm weakest at predicting? Oh, I actually know that one.
I think from a software assisted perspective, a lot of different programs that I personally have used over the years that I've done sleep, because I've used several, we have kind of multi levels of if that, or if X, then Y, right? Because a lot of those are based off of what's been established in the scoring manual, which we talked about before. So those providers have all come together and kind of developed their consensus that we have to have a certain amount of reduction in airflow and you know, for like a hypopnea versus an obstructive apnea. Or when you're talking about maybe a central apnea, a complete cessation of effort in our belt. And so those are all kind of built into those models to really get an understanding of where the software can kind of assist with predicting some of those. But again, going back to what I've mentioned before, a lot of that is really dependent upon kind of those lead placements. A lot of us techs know, you know, as a patient shifts or toss and turn during the night, those belts can move and reposition, and maybe they don't fit as well as we would have liked them to. And so you don't always want to go in there and wake them up at varying points in time, because that may be a critical area in which we're trying to observe how they're sleeping and determine if they've got any type of apnea. I think, Sam, do you want to talk about the AI side of it and kind of how that can also impact with the respiratory?
I know typically, and Sam, tell me if I'm wrong, but I know typically because the algorithm was initially built off of completed studies that were scored by RPSGTs, the weaker areas are the same areas that humans have a harder time. So it does a much better job picking up events, and staging is just a little bit trickier to do, which from what I hear, Mary, correct me if I'm wrong, is also trickier for humans to do. So it still has very high agreement, but typically that's at least what I hear as I'm on the calls with our customers that are using the AI. Sam, is that fair? Mary, is that fair?
Yeah, I think same like you mentioned, even with the staging, that can always be a tricky factor as well. I think technologists, we get really good as time goes on to take into consideration a patient's comorbidities or the medications that they're currently on, and how that's going to affect the morphology of that EEG that we're collecting that's there. And so, yeah, it's going to adjust and it's going to fluctuate a little bit. So, absolutely.
You guys have such great questions. There's like tons and they're all good. Some that are specific to our product, since this is an educational one, I'll answer you guys directly and offline. But Sam, this is a question for you. I think there's been a lot of issues with CPAPs and all sorts of things in the field this year. So I think people are like absolutely looking for help to make it as successful for patients as possible. And the question that came in is, what about using AI with image recognition to try to help do mask fittings?
Yeah, that's a really great idea. I have seen papers where they use 3D MRIs to try to represent the facial morphology of patients to understand whether they might be good responders for something like CPAP or another therapy. So I don't think that that's being used in a broad clinical sense right now, but that is certainly what people have already been investigating.
Perfect. Okay. Some of these are very specific to the product. So just in general speaking, and Sam, I know you're on the AI, you advise the AI committee for AASM, but we did get a specific question. I'm guessing this could be specific to us, but I think in general, having the AI's interests, or the AASM, lots of initials, having the AASM's interest in AI could be a general question as well. So are people working with the AASM to incorporate scoring rules using AI as they, oh no, I'm reading this wrong. Oh, this is specific to us. All right, so I will just ask it. So as the AASM makes changes to their scoring rules, is that something that will be implemented in the AI? Sorry, I read that one wrong.
Yeah, a lot of those ASM, a lot of the ASM guidelines are implemented in more of the if-then rules that kind of are coming out of the core model. So those can be, as certain windows change or different association rules change, those can all be updated. But certainly as it comes to the more core definitions of those event types of those, as those change, the underlying solutions should certainly change with them.
Okay, perfect. And then I think the rest of these are specific except for one. And I'm actually going to take it, but basically the question is, you know, if you're trying to run AI or you're trying to run scoring assisted software, is the data only as good as what is put in is what comes out, and then it says correct, and that is correct, right? And I think that's where Mary was going earlier, that if RPSGTs can rely on the automation to do some parts and really focus on the patient, and you know, she just brought up the example, there's certain things you don't want to wake the patient for because it's probably not going to make a huge difference in the outcome that you're getting, but it should, using some sort of scoring automation should allow you to help, obviously maybe not when the patient's doing an HST, but in particular for a PSG, allow you to really watch those things. We're hearing over and over again that the patients coming into the lab are even more sick than ever before because there is the option of HSTs at home, which we get pretty good data most of the time off of. So really allowing the automation to focus on some things so that you can focus on the patient, and then making sure you're getting as good data as possible, which anybody would need, whether it's running through automation or just an RPSGT taking a look at it. So the answer to your question is correct, but hopefully you know, using some sort of assisted software is going to let you really make sure that the data is good so that you can get good results and accurate results for your patients. So Jason, I will let you wrap it up. Oh, I had one other thing to say because I was doing a bunch of research this morning. If anybody is super interested in this, when I started here, the very first thing I did was research. There's a documentary called AlphaGo, which is super cool. If you want to geek out a little bit on kind of like how AI first started. Anyway, it's just super cool. And then the other thing I forgot to mention, Sam, when you were talking about the cough for COVID, there is a supercomputer that runs AI in Tennessee that when COVID was like baffling people initially, I'm guessing, Sam, you think it was probably a little bit unsupervised, probably because we had no historical data on COVID. They plugged in like 40,000 patient results data from genes to all the EMR, and it took 2 weeks for the supercomputer to just analyze it and then start spitting out some things that they thought, which I just think is super cool. So you could research that as well. It was the supercomputer in Tennessee as it went through COVID. So anyway, I just wanted to get those in if anybody wants to do any research on them.
Cindy, what was that documentary you mentioned?
It's called AlphaGo, and it's I made my son watch it with me, and he didn't think it was as interesting as I was. But if you're starting to geek out on this stuff, it's a really cool start, wouldn't you say, Sam?
I would. It was a big milestone for the AI community.
Yeah. Anyway, all right.
Your son is never going to forgive you for that, Cindy. So okay, so let's wrap it up. So if you do think of additional questions, and I know we had some that we didn't get to today, we'll follow up on those, obviously. But if you do think of additional questions, then email them. So 2 emails will give you team@ensodata.com, or if they're Cadwell-oriented questions, then info@cadwell.com. So team@ensodata.com and info@cadwell.com. So we are right on the hour. Cindy, do you want to close it down? Thank you.
Thanks, everybody. Bye-bye.
Bye.